Hello, I'm Dr. Mark Taylor and I'm a lecturer in civil engineering. So this is Unit 8, and in this unit we're going to look at traction and rolling stock. So this is Unit 8 of the module, and in this unit we're going to look at the locomotives and the coaches, and we're going to look at the differences between electric and diesel traction, and we're also going to look at the main types of train that are available in the UK and Europe. So in this session I'm going to describe the types of passenger and freight rolling stock. We're going to look at the technologies available for electrification of the railway. We're going to outline the technology behind tilting trains. And finally, I'm going to introduce some of the methods used to schedule trains and timetable trains. So by the end of this lesson, you should be able to differentiate between the rolling stock types and specify their advantages and disadvantages. You should be able to specify the technologies available for electrification of a railway. You should also be able to outline the technology behind tilting trains and be able to interpret a railway traffic diagram. So we'll start off by looking at the types of rolling stock. So we're going to start by asking a couple of simple questions. What is a train and why is it important? So a train is one or more railway vehicles capable of being moved. For example, a locomotive with various unpowered vehicles attached to it. A multiple unit could be a set of vehicles providing their own power. They can be used to convey passengers or freight, and sometimes can be mixed. Rolling stock is a collective term for railway vehicles able to operate on the network. So the purpose of a railway is to move people and or freight. Without rolling stock, this would be impossible. The capital cost of rolling stock is very high. Rolling stock has revenue costs, and that includes fuel and maintenance. Revenue from the railway operation should be able to cover these costs. To maximise revenue, the utilisation of rolling stock must be maximised. So there are 6 key themes when considering rolling stock and its use. Fitness for purpose, capital costs, revenue costs, safety, accessibility and utilisation. So we're now going to have a look at what we call locomotive haul trains. So traditional trains comprise of coaches or freight wagons pulled by a locomotive. The train is made up of sufficient vehicles to carry the load, with a locomotive of sufficient power for the weight carried. For passenger operations, one locomotive is usually enough. For freight operations, this number can rise, in some cases up to 4 locomotives, and in some very long trains, for example in parts of the US and Canada, you might see another locomotive placed at some point along the train. Here you can see an example of an American freight train with 4 locomotives at the front, and note the wagons have ISO containers stacked too high. So locomotive haul trains are very flexible. Provided the train weight is within the capacity of the loco, any number of vehicles can be attached. The only limitation is the length of the platforms and sidings. The locomotives should be designed to cover a range of duties. They can be easily swapped in case of a unit failure or changed between diesel or electrified routes.
Please stand clear of the platform edge, fast train approaching.
So at terminal stations, for example with no through line, locomotive hauled services can be inefficient. So when the train arrives, the loco will be trapped at the buffer stops, and the only way to release it is to use another loco to remove the train. The problem can be partially alleviated by providing a runaround track and associated S&C. However, this takes up valuable space in the station and also increases the turnaround time. So for a fixed formation train with even intervals, it's desirable to drive the train straight back out without moving the locomotive. And a cheap way of achieving this is using what was called the push-pull operation concept. Push-pull means that some form of control is established at the rear of the train. And this has the benefit that formations can still be varied easily if demand changes. The earliest form was converting the rear of the last coach to a cab with remote controls for the locomotive. More recent forms have special rear trailers known as driving van trailers or DVTs. These are dedicated rail vehicles with a cab plus an area for luggage, cycles, etc., but no tractive power. Generally, passengers are not permitted to ride in these vehicles at speeds over 160 km per hour. Another form of push-pull uses two locomotives, one at each end of the train, for example, the Channel Tunnel Shuttle or the UK Intercity 125. The two locomotives are necessary to provide sufficient power to the train. So we're now going to have a look at what we call multiple units. So locomotive operation of intensive services is very inefficient, with push-pull services also having their limitations. Multiple unit operation was a response developed initially in the US on metro systems. So multiple units spread the traction system along the train instead of housing it in a bulky locomotive. So the power units are distributed underneath the floors of several vehicles in the train, and these are then controlled by the driver in the cab. Electric multiple units were the first to be developed, but eventually diesel multiple units followed later. So multiple unit trains are made up of vehicles which must be of the right type and coupled in the correct position in the train. Tractive power is usually distributed under more than one vehicle, and control is provided for all units from the driving cabs, and there's a cab at each end. So vehicles in multiple units are usually referred to as cars. Powered cars are known as motor cars, or trailer cars if not powered. So multiple unit trains are formed from sets of two or more cars. These sets are semi-permanently coupled together, only being uncoupled inside a depot. Some operations require two or more sets to be coupled together to provide capacity appropriate for the service. Trains can be lengthened or shortened whilst in service by adding or removing units. However, unlike a local hauled service, the entire train is taken out of service for maintenance. So traditionally, multiple unit trains were only used in high-density suburban operations. In such applications, demand is high and a fast turnaround is required. More recently, long-distance traffic has shown the same tendency. And in the UK, we have the Pendolino, in Japan the Shinkansen, and in France the TGV, and these are all multiple unit trains. So we're now going to examine what we mean by fitness for purpose. So fitness for purpose depends on the intended use and can include the maximum speed and acceleration of the train, the number and position of the doors, the seating pitch and the width, whether there's standing or sitting accommodation, for example in an underground train or a long distance train, provision for luggage storage, toilet facilities, provision for seat reservations. We might also need a buffet car or trolley service. We might have some tables. We could also separate first and second class. And everything has to be cleaned easily. We may also have a requirement for air conditioning and ventilation. And in more modern times, we've seen the rise of people needing laptop charging facilities and also Wi-Fi communication. So here we can see two examples of interiors in intercity trains. So, due to longer distances, we've got comfier seats, armrests, lots of luggage storage overhead and at the end of each coach. So here we can see the inside of a regional train, and we can see that the seat coverings are different, they look a bit more robust. The spacing of the seats is different, the layout of the seats is different as well with tables. We can see there's also some overhead luggage storage area, but it's not quite as extensive as the Intercity train. And here we can see the interior of a suburban regional train. Again, very robust, seat coverings, lots of plastic used as well, easy to clean, tables provided. Spacing different though. Notice the layout of the seats, there are more seats in this coach. Here's an example of a commuter suburban train in Denmark. You can see the layout's very different. So we're still on the commuter train in Denmark. Here we can see an area that's dedicated for storing bicycles, for people with prams, with pushchairs, or in wheelchairs. Sleeper trains are quite efficient because they sit idle during daytime hours. A Couchette train offers the best of both worlds, so seating by day and an accommodation for up to 6 berths at night. However, you don't have quite the same privacy in the facilities as you do on a sleeper train. So I'm now going to have a look at passenger safety in rail vehicles. So many safety systems in the railways are provided by the actual infrastructure, and examples of track safety systems include interlocking and train protection systems. However, the design of the rail vehicle itself is also critical, and safety issues include crashworthiness, emergency evacuation, and fire protection. So if you go back to the Greyrigg accident report of 2007, we can see that the train performed better than earlier designs in previous accidents. The passenger and crew areas were not significantly compromised. However, only 2 windows did not fully retain people within the carriages. The bogies also did not separate from the carriage bodies. However, the RAIB considered that safety could be improved in relation to the design of seat mountings and the lighting panels above the seats. And these were associated with recommendations for the study of rail vehicles and rollover. So I'm now going to look at the subject of accessibility in railway passenger stock. So the rail vehicle accessibility regulations have applied to all new rail vehicles entering service since 1998. What the regulations did was standardise the requirements to meet the needs of disabled passengers. And this included issues such as access for wheelchair users, the size and location of handrails, handholds and control devices, and providing passenger information systems. So, all rail vehicles had to be accessible by no later than the 1st of January 2020. In July 2008, a new European standard came into force, and this was the technical specification for interoperability for persons with reduced mobility. The PRM-TSI applies to all trains used across Europe, and it sets standard for accessible trains, stations and other facilities. So we're now going to look at the subject of electrification. So the first electric locomotive was developed by Siemens. It was demonstrated at a Berlin conference fair in 1879, and it was used for transporting visitors around the fairgrounds. It was operated using a DC motor and had a live rail between the running rails, and its maximum speed was 13 km per hour. Here we can see the train itself and details for the patent, and also, lower right, a version where overhead line electrification was used. So the first electrified railway was the Baltimore and Ohio Railroad in the US, and it was opened in 1895. It was operated using a 675 volt DC overhead system, and it was developed to address the problem of smoke in tunnels. Electric locomotives were also used on the London Underground. For example, the City and South London Railway used electric locomotives when it was opened in 1890. So direct current systems were simple to manufacture, but they had a practical limit of 1500 volts, and this was due to the commutator bar. So electrification was limited to tramways and commuter railways. Issues regarding the transmission of electrical supply using DC systems was also impractical, so there was a need to develop an AC motor. So various experimental prototypes were developed in Germany. These ideas were then refined in France following World War II. The system was based on 25 kilovolts running at 50 Hz, and this facilitated longer distance and higher speed, and this is what made the Japanese Shinkansen trains viable. So some of the benefits of electrification include lower energy costs, greener energy, provided electricity is generated in a sustainable fashion, lower noise. They can also feature energy recovery systems whilst braking. The trains are generally lighter, so they have a greater power to weight ratio. They can accelerate faster, and they require less maintenance. So there's a couple of different ways we can electrify the railway lines. The first system is called third rail, and this is mostly a DC supply system. So this features a conductor rail mounted on ceramic insulators, and the trains have a metal contact block known as a shoe. And the position of the contact may be above, beside, or beneath the rail, and the current is returned through the running rails. So at the top of this image you'll see the fourth rail system, and that's where we have running rails with a positive rail to the right and then a negative rail in the centre. And the bottom of the image shows a third rail system where we have the top contact on the outer rail or the underside contact next to the outer rail. And here you can see two examples of fourth rail and third rail systems, and you can see that the switches and crossing units, this becomes quite complex. Another method of electrification is the overhead line equipment system, or OLE, and this is an AC supply system. So electrified lines provide power. The lines are suspended above the track by catenary systems, and the trains feature roof-mounted collectors called pantographs, and the current is returned through the running rails. This figure shows all the components in the OLE equipment. This figure shows the various electrification systems that are used across Europe. So a third rail system has a number of benefits. It generally costs less than an OLE system because there's no catenary equipment required, no modification of structures, for example bridges, etc. And it's cheaper to maintain. It's also less susceptible to damage by wind, and it has less visual pollution, if you like. So the disbenefits of a third rail system include the high risk of electrocution. As high voltages are unsafe, high current is needed, therefore there's high losses. So it's not suitable for long distances. And there's also limitations on train maximum speeds. So there's a number of benefits of using OLE. The first one is a lower risk of electrocution, and that's because the power supply system is away from the areas of human occupation. We also use alternating current, or AC, which means that we can transmit the electricity over longer distances. The trains can also travel at higher speeds. So, in terms of applications, third rail is generally used where distances are short, higher speeds aren't that important, and prevention of electrocution is possible. So therefore used in metros or suburban rail situations. Overhead line electrification is generally used for longer distances, where higher speeds are important, and there's little or no control over electrocution risk, and therefore they're used for regional or high-speed rail routes. Here you can see a photograph of the Copenhagen metro system. It uses third rail, and the third rail uses an underside contact just to the left of the running rail. The Copenhagen metro has two measures to reduce the risk of electrocution. The first one is the glass doors on the platform, and these only open when the train is actually at the platform with its doors open. You'll also note that the track away from the cities is elevated, and this again separates people from the track. So here you can see the extent of the OLE equipment at Glasgow Central station. So back in the day, this is how we used to maintain the OLE equipment. So modern OLE maintenance techniques use road rail access platforms. And it's not clear from this image, but the operatives standing in the platforms have harnesses on, and they're also connected to the cage that they're standing in. So there's a broad range of road rail plant that we can use. it's a good idea to spend some time looking at a manufacturer's or plant hire company's equipment specifications. So this is Unit 6, and in this unit we're going to look at switches and crossings. So now we're going to have a look at the subject of tilting trains. So if you remember back, passenger comfort was based upon equilibrium cant. So if we increase the velocity, we must either change the radius or the equilibrium cant. Therefore, high-speed rail is likely to feature large radius curves and increased cant. But what if conditions are such that we can't achieve large radius curves and we already are at the limit of cant? So this was the problem with the West Coast Mainline in the UK. The existing alignment was not easily adjusted, and the proximity to other infrastructure would also create serious engineering challenges. So higher speeds around curves can also be achieved by using a tilting train. For a given velocity v and a radius r, tilting will increase the component of the vehicle's weight and decrease the component of the centrifugal force. But note that the total forces remain the same. So the total forces remain the same. So if TC is reduced, then PC must increase. Therefore, tilting trains result in greater stresses in the track. So track wear is going to increase, and subsequently the formation needs to be upgraded. So back in the 1970s, British rail engineers started out on the Advanced Passenger Train project. So the Advanced Passenger Train was a tilting high-speed train developed by British Rail in the 1970s, and it was to be used on the West Coast Main Line. The APTE achieved a British Rail high-speed record in 1975 of 152.3 miles per hour. The APTP achieved 162.2 in 1979, and that record stood for 23 years. But the problem with this project was that the development of the prototypes dragged on. Eventually, Thatcher cut the funding for the project, and facing possible cancellation of the project, BR decided just to release the prototypes into service. The result was a media circus with every problem, large or small, front page news. The trains were later withdrawn from service again, and to the great amusement of the press. The problems were eventually solved and the trains quietly reintroduced in 1984 with much greater success, but by this time the HST was dominating cross-country rail services. So you can see the final version of the APT train as it operated in 1984. So eventually the British Rail Class 390 Pendolino was introduced. This was an electric multiple unit that used the Fiat Tilting Train Pendolino technology and was built by Alstom. 53 units were originally built between 2001 and 2004, and they were used on the West Coast Main Line. They were ordered as 8-car sets and later extended to 9-car sets, of which some were then lengthened to a further 11 carriages. So in a tilting train, we've got to maintain gauge clearance, and this can result in reduced overhead storage space or headroom, and space for the tilting mechanisms may also result in a higher vehicle floor. So tilting is achieved by a mechanism under the vehicle floor. The tilting mechanism is either active or passive. In the UK, tilting is activated by the Tilt Authority and Speed Supervision System, or TASS. Tilting trains are still prone to derailment if curves are taken at excessive speed. For example, here you can see one that derailed in Australia in 2004. So we're now going to have a look at schedules and timetables. So schedules aim to determine the following information for each train: the days on which the train should run, the route the train is guided through the network, the arrival and departure times, and the maximum speeds. So a timetable is a survey of all scheduled trains running on a line. It's a part of the railway operation that's most readily understood by the passenger, and it only contains information the passenger is likely to need, e.g. departure times, arrival times, and station stops. So now we're going to have a look at the subject of understanding the use of the network, and we do that using what's called traffic diagrams. So to plan and operate a railway, we need to understand the use of the network at any one time. So the traffic diagram is the most common means of displaying this information. Traffic diagrams take the form of a time-distance diagram. So there's two axes, a time axis and a station axis. The stations are on either the horizontal or the vertical axis depending on locality. So every station, there's a station line parallel to the time axis. Train movements are shown using train paths. Train paths are time-distance graphs showing the passage of the train in space and time. And the train path will usually feature a train descriptor. At intersections of train paths and station lines, a time is shown. Here you can see a traffic diagram for the simple route shown at the top of the figure, showing the train paths, showing the time-distance graphs if you like, the train descriptors, and also the times of intersection. Additional diagrams can also be prepared for station movements. Each track at a station is represented by a line parallel to the time axis. Tracks are usually allowed movement in two directions, so the direction of movement is shown on the diagram in addition to platform occupancy. So you can see a traffic diagram for the station platforms, tracks 11, 12, 13 and 14. But note the symbols on the right. You can see which trains are stopping, which trains are scheduled to stop, and which trains terminate, for example. So that's the end of Unit 8. The next unit we're going to look at rail management and maintenance. So thanks for listening. Bye for now.